Okay.
Yes.
Then
Today, I have to give a lecture on Lindemann theory of Lindemann theory of unimolecular reaction of unimolecular reactions. We know that a chemical reaction takes place by collision between the reactant molecules. In a bimolecular reaction, where two molecules are reacting, there is a collision between two molecules. For example, suppose we have an elementary reaction of this type, 2A product. Now here, two molecules of A are colliding with one another. And as a result of this collision, the bond breaking takes place. Now the rate of this reaction, since two molecules are taking place, so rate, and this is the elementary reaction, so according to law of section, the rate of this reaction, the rate of formation of P, that is rate of reaction, must be proportional to the molar concentration of A power 2. This is that is, the order is 2. Thus, a bimolecular elementary reaction, which is bimolecular, it must obey second order kinetics. That is, the rate of reaction must be and must depend upon must vary with the square of the concentration of the reactant. The order should be 2. Similarly, for the 10 molecular reaction of this type, 3A product, suppose here collision between three molecules of A are taking place. The rate of reaction will be given by dP by dt. This is also an elementary reaction proportional to concentration of A power 3. Here order is 3. But discovery of first order reaction. Discovery of first order reaction. First order reaction. First order unimolecular reaction like this. Unimolecular reaction. For example, suppose let us consider this reaction PCl5, PCl3 plus Cl2. Here, the rate of reaction, that is rate of consumption of PCl5 by dt, this is proportional to concentration of PCl5. That is, it is the first order reaction. The order is 1. The order is 1. Now, if order is 1, this one molecule is involved in the reaction, then how does collision take place? Because you know that reaction must occur by collision between the reactant molecules, which is necessary for the breaking of bond. Then how does this reaction take place? That is, the discovery of first order unimolecular reaction created a paradox in chemical kinetics. Paradox in chemical kinetics. How does a unimolecular reaction occurs where there is one molecule, and how collision is possible? The explanation was given by Lindemann, and therefore it is called Lindemann theory of unimolecular reaction or collision theory of unimolecular reaction by Lindemann. Now, according to Lindemann theory of unimolecular reaction, and a unimolecular reaction, a unimolecular first order reaction, also takes place by bimolecular collision. Just note down that that a unimolecular first order reaction also occurs by bimolecular reaction. Suppose we write this A product P Now, although this reaction is the first order, the rate of reaction varies as the first power of the concentration of A, but this reaction also occurs by collision between two molecules of A. By collision between two molecules of A. So unimolecular reaction also occurs by bimolecular collision. Then the question arises, if it occurs by bimolecular collision, then the order of reaction should be what? Then the order of reaction should be two. But here the order is one. Here the order is one. dA by dt. This concentration of A, that is the rate of consumption of A or the rate of production of product, that is the first power of the concentration of A. Then it is the first order reaction, although it is taking place by bimolecular collision. The theory was given by Lindemann. Lindemann suggested that although a unimolecular first order reaction also occurs by bimolecular collision, but the activated complex, that is high energy reactant molecule form as a result of bimolecular collision, does not decompose into the product immediately. Rather, there is a time lag between activation and decomposition into the product. And during this time lag, the activated molecule, that is high energy molecule, form as a result of collision, may collide with some energy poor molecule, and in this way, the energy of the energy rich molecule, will be robbed off by the poor molecule, and again, the activated molecule will become deactivated. That is, the theory, he gave theory like this. In the first state, A plus A, collision between two molecules of A takes place, and when molecules, there is a collision means a redistribution of energy. There is a redistribution of energy. Yes, there is a redistribution of energy. And in the redistribution of energy, suppose this A gives energy from this molecule. So the energy of this molecule will decrease and the energy of this molecule will increase. So A will become an activated molecule. This is activated molecule. Activated molecule plus A. Activated means high energy molecule. This molecule has got sufficient energy to convert into product. But according to Lindemann theory, this A star does not decompose into product then and there. Rather, it is staged for some time. And that, in other words, there is a time lag between activation by collision. When two molecules collide, there is a formation of activated molecule. This is called activation reaction. So, according to Lindemann, there is a time lag between activation and decomposition of activated molecule into product. And during this time lag, this activated molecule may collide with some energy poor molecule, and in this way, during this collision, its energy will be taken away by the poor molecule and it will become again deactivated. So, in other words, this activation is a reversible process. It's a reversible process. This is activation and this is deactivation. Activation and deactivation. Deactivation. Suppose the rate constant of activation is K1 and rate constant of deactivation is K minus 1. That is, activation is a reversible process. And in the second state, now suppose this A star with this bond may collide with energy poor molecule to become deactivated, and a activated molecule may be fortunate enough to survive the time lag, and then that molecule may convert into the product. In other words, that although activated molecule converts into deactivated one by polygon with energy poor molecule, but but there may be some activated molecule which would survive the time lag, and by doing so, it will be able to decompose into the product. So this A star, this is lucky A star, because it could not collide with the energy poor molecule, then it would convert into the product P. So this first order reaction, this is the first order reaction, AP. Here the rate is minus dA by dt proportional to concentration of A power 1. That is order is 1. Order is 1. So this unimolecular reaction, which is first order, according to Lindemann, occurs according to this mechanism. The rate constant of this reaction is K2. Now, according to this mechanism, the rate of reaction will be rate of formation of P. So, rate of reaction, that is the rate of formation dP by dt. This is proportional to concentration of A star, that is activated complex. And this is on plus dP by dt. This is equal to K2 into A star. A star. This is equation number 1. Equation number 1. Note that K2 is the rate constant of the composition of A star into product. Okay. So this. Now the concentration of A star, has to be evaluated. So this can be done in this way. Now see, the rate of A star is for in A star is for in the forward reaction, forward state of state 1. State 1. So, so rate of its formation. So rate of its formation is given by plus d star by dt. This is proportional to A into A, proportional to A into A, that is A square, and proportionality constant is K1. So this is equal to K1 into concentration of A square. This is the rate of formation of A star. And the A star is decomposed. The A star is consumed in this state. This is the backward state of state 1 and also in the state 2. A star is consumed in the backward backward step of step 1 and in step 2. So its rate of consumption is given by minus dA star by dt. This is k minus 1 into A star into A, the rate of this backward reaction in which this A star and A are taking part, and plus this is k minus 1, sorry, this is k minus 1, and again k2 into A star. Here A star is consumed in this step, and so the rate of this step will be K2 into A star concentration. Okay, now this is now in the steady state, according to the steady state, in a steady state, what is the steady state? When a steady state is whenever a reactive intermediate is formed in any chemical reaction, whenever a reactive intermediate is formed in any chemical reaction, the concentration of intermediate goes on increasing, but soon it becomes constant. This is because the rate of its consumption equals to the rate of its formation. And then there is no increase in the concentration of reactant, in the concentration of the intermediate, it becomes constant. So in the steady state, the rate of in the rate of formation of A star must be equal to rate of formation of A star must be equal to the rate of formation of A star. So in this rate of formation of A star must be equal to rate of consumption of A star. Consumption of A star. Rate of consumption of A star. So we have, therefore we can write that this is the rate of formation and this is the rate of consumption. So this must be equal to, that is Q1A, Q1A is equal to K minus 1 A plus into K minus 1 A star into K plus K2 into A star. K2 into A star. Okay. So, and therefore, K star taking common, this is equal to A star concentration, this is equal to K minus 1 A plus K2. And then A star is equal to A star equal to K1A by K minus 1, sorry, K minus 1A plus K2. Now putting this in equation 1, this, we get the rate law of the equation. So we have so putting this in equation, putting this, putting the value of A star, A star equation in equation 1 mentioned above, mentioned above, we get plus dp by dt. This is K2 into K1, K2 into A star is this. So this is K1 into K2 into K2 into A divided by K minus 1 A plus K2. This is the equation 1, 2. This is the rate law of the reaction. This is the rate law of, of a unimolecular reaction. A unimolecular reaction. Here, two cases arise. Here, two cases arise. Case one, when concentration of A is very large, is very high, or pressure of gas A or pressure of gas A is very high. Same thing, because if concentration, if suppose A is a gas and the pressure of gas A is high, this concentration will be high. Now, under this case, what will happen? Suppose this is a container, and in this container, there are the concentration of A is large. That is, A molecules are thickly populated like this. A molecules are thickly populated. The intermolecular distance between them will be very small. Will be very small. Like this. Now suppose this molecule is, suppose it is coming toward this. Suppose this molecule is activated molecule. This molecule is activated. And this is not activated. This is energy poor molecule. It is coming toward this molecule. And suppose it takes 2 seconds for this molecule to come at this point. Whereas suppose the time lag is what? The time lag is 5 seconds. That is, this activated molecule will decompose into product after lapse of 5 seconds. It will have to wait for 5 seconds before converting into the product. And this energy poor molecule is colliding with this molecule within 2 seconds because it takes only 2 seconds for this molecule to come at this point. This means this molecule will not be able to survive. This molecule will not be able to survive with time lag and it will be deactivated. So that is to say, if the concentration of reactant A is very large, then the chance of deactivation will be large and chance of decomposition into product will be very small because most of the activated molecule will deactivate it. So what will happen? In this case, deactivation will be large. Deactivation rate constant is what? K minus 1. So in this case, K rate of deactivation will be far more than the rate of decomposition of the reactant into product. So this is larger than this. And and concentration of A is also large, also large. So so K minus 1 A is far more than K2. So K2 can be negative in comparison to what? In comparison to K1A. In comparison to K1A. That is K minus 1A, K minus 1A plus K2. This is approximately equal to K minus 1A, K minus 1A. Now, putting this approximation, putting this approximation, putting this approximation in equation 2, we get plus dP by dt. This is equal to your K1 by K2, K1 into K2 by K minus 1 A. That is proportional to this means so this means what? dP by dt. So K1, so dP, the rate of formation of product will be proportional to concentration of the order will be how much? The order is 1. So when the pressure of gas is low, A is high, the concentration of A is high, then the reaction will obey as the first order reaction. Will obey as the first order reaction because this is the rate expression for the first law. Now the another case is, the second case is, one thing, this K1 2 by K minus 1. This is the rate constant. This is the rate constant of, the reaction, which is first order, which is first order. This is the rate constant of reaction. Now again, suppose we are just considering the second case, the case 2. This is where concentration of A concentrated, that is pressure of gas A, or pressure of a gas A is very large, is very low. In this case, this situation can be depicted as, suppose this is the container, and in this container, the reactant A is enclosed, the concentration is very low. This means the molecules of A are far apart from one another, like this. The molecules of A are far apart from one another. Now, let us suppose that this is the molecule. Now, for this molecule to come here or this molecule to come here, any neighboring molecule to reach at this point, suppose it takes 7 second time. And time lag, and suppose time lag is 5 seconds. Now time lag is like that, that is this activated molecule will survive only up to 5 seconds. After 5 seconds, it would convert into product. And this molecule will be able, or this molecule, or this molecule, or this molecule, or this, will be able to come here after after 7 seconds. It will take 7 seconds for this molecule to arrive at this point. So before this molecule will be arriving here, this activated molecule will be converting to the product. So the question of deactivation will not arise. So in such a case, the situation will be just the reverse. Here here rate of decomposition, rate of decomposition of A star into product P will be will be more than will be more than that of its deactivation. So K2 is greater than K minus 1. Also, since concentration of A is low, so K2 will be far more greater than K minus A. Thus, K minus 1 A may be neglected in comparison to K2. So K minus 1 into A plus K2, this is equal to K2. Putting this approximately, putting this in equation 2, we get what? We get this is negative comprehension this, that we get plus dp by dt is equal to K1 into K2 to A by K2, and this is equal to K1 into A. So plus dp by dt, this is equal to what? proportional to concentration. Oh, sorry, what I've done some mistake. Oh, K1 into K2 squared. Sorry, here this should be a square. Yes, sorry, here it should be a square actually. I committed a mistake earlier. Here it is a square here. So K1 into K2 squared, this is squared, and then this is plus dp by dt. This is proportional to concentration of A squared. Now the order is 2. This Q1 is the second order rate constant. Second order constant. Thus, we see that A, we see that when there is a collision between two molecules in any reaction, that is, there is a bimolecular collision, two cases will arise. The deactivated molecule will will get deactivated, meaning more than it will convert into the product. And in such a case, the reaction will be a first order kinetics. And second, if the rate of decomposition of the activated complex into product is more than the rate of deactivation, then the reaction will follow second order kinetics. That is, reaction will be second order. This is the Lindemann theory of reaction rate. The Lindemann theory of unimolecular reaction. Okay, this is all about. This is all about Lindemann theory